Okay, hello everyone. I'm the founder of InfiniteFlow, and today it's my honor to introduce our open source software, RAGFlow, to our new friends. So today my presentation is divided into these parts, and before I start the introduction, I make a survey. So does anybody heard RAGFlow before? Oh, cool. Okay, so let me start. So this is how RAG works. Simply speaking, the RAG could be divided into 4 parts. We have the trunking and indexing and retrieval and generation. So for any applications such as agents and many other conversational AIs, they can be looked on as an application built on the RAGs. Yes. So the applications could ask the questions, and the questions will be changed into embedding, and to get the relevant chunks, and then they got the final answer according to the relevant chunks. So such a pipeline is pretty simple, and there are many open source RAG softwares. So they look on this pipeline as an orchestration. Yes. So within many enterprises, we can set up such kind of a pipeline within maybe half an hour, just for POC usage. However, if we want to use a RAG in our enterprise truly in production, maybe it will take us for several months. So RAG is pretty complicated. Why? According to our summarization, we can conclude that at least there are 3 kind of challenges that current RAG has met. First of all, if these documents are not pure text, if we have PDF documents such as multi-modal PDFs, and we have figure diagrams, and we have tables, formulas. So if we have we just use a naive trunker, then we will get garbage in. So for garbage in, we will get garbage out. The first challenge. For the second one, most of the RAG use vector database for the retrieval and recall. However, we conclude that vector database is not suitable for enterprise-grade RAG. Why? Take care of such 3 sentences. The first one, the GDP or the revenue of the Guangdong province in China in March 2025, the first one. The second one, the GDP or the revenue of the Guangxi province in China in March 2025, the second one. For the third one, still the same, the GDP or the revenue of the Guangdong province in China in April of the 2024. These 3 sentences, as a human being, we know they are totally different. However, the vector similarities among these 3 sentences are pretty close. It means that a single vector cannot differentiate it. So within enterprise, this cannot be tolerated. So a pure vector database will lead to a low hit rate. So the second challenge. For the third one, we can see that RAG is actually an upgrade of our old enterprise search engine. So we ask the question, and then we find the corresponding similar chunks according to the question. It means that we can find the answer according to the question. However, it's not true in many situations, such as we have some query-focused summarizations, such as, tell me about the question. Oh, sorry. Tell me what this PDF has talked about. You cannot find the answer according to such kind of question. It's a query-focused summarization. And also, we have some other complicated questions, such as a multi-hop question. The multi-hop question is pretty complicated, that the answer for such kind of question is actually a summarization based on the answer of several sub-questions. So we cannot directly search the results according to the question. So 3 challenges. First one, garbage in, garbage out. Second one, low hit rate. Third one, semantic gap. So how do we do that? So this is the architecture of RAGFlow. And then first of all, we train a series model, and we call it deep document understanding. We use this model to parse the multi-modal PDF documents. Firstly, we got the document layout, and we recognize the coordinates of each figure, table, formula, and so on. And after we get the document layout, if the content within the coordinates comes from the table, belongs to a table, we use another table, another model, such as a table structure recognition model, and to convert the image into the text. Then we got the clean chunks. So we use the deep document understanding models to change the garbage in into quality in. So the first one we have done. And after we have got chunks, we have embedded or integrated some other solutions to named as a document pre-processing, such as we use a graph RAG to extract the knowledge graph. And also we have provided Raptor. Raptor is a kind of document clustering techniques. And also we have a contextual retrieval, which is presented by cloud. Yes, so all of these solutions, in essence, it's to use LLMs to bridge the semantic gap between question and answers. So after this pre-processing, we can say that the only left question is how to improve the low hit rate. So how do we do that? Actually, we wrote a database, start from zero, start from scratch. This database is dedicatedly designed for RAG. So besides vector search, we have also many other search, including full text search. Full text search is necessary for enterprise-grade RAG because it is the only approach to differentiate the three sentences that I mentioned just now. And also we have also sparse vector index. We even have tensor index. So what's tensor mean? I will explain later. So we wrote a database just for RAG usage. In summary, we have a series of models for extraction to resolve the garbage in, and we integrate some other techniques such as graph RAG, which is invented by Microsoft, and we have improved it, and some other Raptors for pre-processing, and this is used to bridge the semantic gap. And then we wrote a database named Infinity just for the low hit rate. So RAG is pretty complicated. RAG does not mean LLM ops. RAG is not a problem of orchestration. It's much more. So this is our open source. So RAGFlow was open sourced in the April day in 2024, but the open source of RAGFlow is not full. So we can see that currently we have got 51,000 GitHub stars in more than 1 year. And among all of the star users, nearly around 49% comes from China, followed by 11% from US, and 5% from India, and then 2% for Germany, 2% for Brazil, and then France. So I hope more users from France will give us star from today. Okay, so another GitHub star trend is the Infinity. So you could see that it's only got 3,000 GitHub star. So Yingfeng compared with some other models or applications, it's much more, it's less sexy. So just like the small room, so many such less guys. So however, without Yingfeng, without any applications. Okay, so this is the introduction. And for this diagram, it's a comparison made by our partners. The scenario is to provide a question answer for the bank customer service. Yes. And we compare the open source version and the enterprise version for RAGFlow to some other, such as naive RAG and some commercial RAG products. So what does naive RAG mean? Naive RAG is just this diagram. Yeah, this is naive RAG. So naive RAG means LLM ops, means orchestration. RAG is not orchestration. And here we have two metrics. The first metric is totally correct. So what does totally correct mean? Because in this scenario and this test, we have got several items for each question. So if the LLM gets the answer without less, without more, they can call it totally correct. And also, we have partial correct. So given the naive open source RAG solutions, we can only got 15% for the totally correct. So it's pretty low. It means that with the garbage in, we have garbage out. and we have low hit rate because of the vector databases. So we need a total solution. That's RAGFlow. Okay, so let's come to next section, the chunking. How do we do chunking? This is our how our deep doc works. It's a series of models. So given the multi-model PDF or images, firstly, the entry of the deep doc is a model called document layout analysis. Document layout analysis is actually an object detection to recognize the coordinates for the paragraphs, title, page head, page foot, formula, table, and image. And if the content with the coordinates belongs to the text, so we come to this pipeline. And if the image, if the content within the coordinates belongs to image, we just crop, and the users could choose to send the image to VRAM, to multi-model language models, to get the text description, and then we index the text. And for table, it's similar. However, we use a dedicated model named the table structure recognition model, and then we build it into chunking. So table recognition is much more complicated than others. This is our screenshot. So we ask any users to, we permit each user to see the chunking result. On the left side of this image, it's a preview of the raw document, raw PDF document. And on the left side, we ask every user, we let every user see the chunking result. And the chunking result, if he is not satisfied, or if he want to add some more meta information, he can modify it. For table structure recognition, it's pretty complicated. Why? Because we need to correspond each cell to the head of the table. However, you could see that within this cell, there are many cells and without borders, and there are many cells can be merged together. So how do we correspond the cell content to the table head? It's pretty complicated. And even we have some other situations such as a table with cross page. All of these cases should be judged by the table structure recognition. So how do we do that? At first, we just use a CNN network to train the model. It looks like it's not sexy. Just CNN. However, several months later, we want to use some more sexy approaches, such as transformer to generative models, and we use this one. We got a good result. For example, we use VAE, variational autoencoder, to train to get the codebook, and then we use this codebook to train the transformer encoder, and then we use the trained transformer encoder to train the end-to-end transformer encoder decoder. So given the table image in, we got the HTML text out. However, we abandoned this approach eventually. Why? It's too slow. Given a table, maybe we have about 1,000 tokens. So we need nearly 1 minute to generate the text of the single table. It's very, very slow. Given a CNN or the not so sexy model, we just use tens of milliseconds to finish the parsing. So currently we still use CNN. However, in future, I think this should be true. We could use a series of united document understanding models. So this model should be based on the VRM, and no matter within the image, it contains table, flowchart, pie chart, bar chart, and so on. All of these images could be changed into HTML. However, currently, at least for table content, the precision is pretty low. So none of the VRM currently can convert the table into the text that can guarantee the structure of the table with a high precision. However, we are an engineering company, so we will integrate any approaches, no matter it can be used currently or in future. So how does the multi-modal RAG work now? Actually, we have resolved part of the multi-modal RAG right now. So we have a series of solution paths. The first one is to just now what I have mentioned. Given the image or PDF documents, we have got the object detection and the document layout. If the output is text, just OCR. If it's a general image, we can send to VRM and got the text. And also, we can also send this image to VRM and got the text. So these three paths have already been available in RAGFlow. However, we can do more. For example, you could see here and here. Given the image, we change it into the tensor using the COL XXS. So what does this mean? I will explain more. Okay, so let's do next part, retrieval. Retrieval is much more complicated. For retrieval, we wrote a database named Infinity. Infinity is actually a kind of index database. So what does index database mean? It's actually a column store. So according to different data types, we build different indexes. For example, given numeric or some dimensional fields, we build the secondary index, so which is used to provide very fast range filtering. And given dense vector, we can build a vector index. Given sparse vector, we can build sparse vector index. Given text, we can build a full text index. So this is all necessary. And given tensor data, we have already also provided tensor index. I will explain the tensor index later. So actually, Infinity can let you to assemble at your choice. You can assemble single one, two-way hybrid search, three-way hybrid search, and four-way if you like. So it is the most powerful database and can provide the hybrid search right now. And maybe you want to ask, what's your performance? So this is for performance comparison. We just use a single function of Infinity compared with some other databases. For example, we compare the vector search of Infinity to the vector database, such as Quadrant. And we also compare the full text search of Infinity to Elasticsearch just for full text search. And on the left side, they are query latency. On the right side, they are QPS. So you could see this diagram is got from the GitHub, and you can reproduce the result according to our script and the data in the GitHub repo. So let me introduce hybrid search right now. What does hybrid search mean? Hybrid search means we will search for the data using one or several approaches. In this diagram, we evaluated on the dataset named MMDR, and the metric is NDCG at top 10. Here, on the x-axis, BM25, full text search, dense vector search, sparse vector. So vector search is the lowest. So it means a pure vector store will have a low hit rate. And from here, we have two-way hybrid search. So this dense vector means vector search plus sparse vector and plus RRF. RF is a kind of naive fusion because we have two kind of search approaches and we need to fuse the results together. So RF means reciprocal reverse fusion. It's pretty simple. And for this one, full text search plus vector search plus RF. And from here, we have got the three-way hybrid search plus RF. For all of these results, you can find that in the paper in this way. So this paper is published by IBM Research named Blended RAG. So this paper is published 1 year before, and at that time, there does not exist a database can provide a three-way hybrid search, and after 1 month later, Infinity could provide. However, from here, the last one from the right side, you can see the result is much better. Why? Because we changed the re-ranker from the RF to ColBERT re-ranker. So what does ColBERT mean? Here is how to use ColBERT to improve some other recalls. Full text search plus ColBERT, vector search plus ColBERT. So you could see that no matter what kind of hybrid search you are using, if you attach the ColBERT-based re-ranker to the hybrid search, the result could be improved a lot. So what does ColBERT mean? ColBERT means context late interaction model. So what does late interaction model mean? Let me introduce more. In this diagram, we have three kinds of architecture for the retrieval during RAG. The first one is actually the vector search. It is named as a dual encoder. Dual encoder means we encode the query and the document chunks separately. We just use a transform encoder and then the text is encoded into several embeddings. For each token, we have corresponding embeddings. However, the output for this transform encoder is just a single vector. And then we have got the vector search. We compute the similarity between the query vector and the document trunk vector. We got the inner product to compute the similarity. This model have two shortcomings. The first one, it will cause semantic loss because we have only single vector output as an output. However, we have generated many embeddings for each token. The second one, we cannot capture the token interaction between query and the document trunks. The interaction we cannot capture. So this means that given pure vector-based search, the recall is pretty low. In the middle of the diagram, it means a cross encoder. Actually, the model is almost the same with the left one, except that the input for the model is a pair. We pair the query and the document trunk as an input, and then within the model, we capture the token interaction. So it does not have any semantic loss, and we can capture the token interaction, and we just output a score. That's why the re-ranker can perform much better compared with a vector search. However, this approach has also some shortcomings because this requires a model inference. So we can only perform the document re-ranker using GPU, and because of the performance degradation, we can only use to top 10 or top 20 for the model inference. So it's pretty slow. And for late interaction encoder, it's pretty similar with the middle one, but the working flow is totally different. We store the embeddings for each token during the indexing. So it means that the most of the computation have already been finished during indexing. During the online retrieval, we just encode the query into a series of embeddings. So what does tensor mean? Here, tensor means we store each embedding for each token, and we represent a document chunk with a series of embeddings. So this means multi-vector, also tensor. So we use tensor in late interaction models. We use tensor to represent each query, to represent each document trunk. And then during the online retrieval, we just compute the pairwise token embedding similarity and accumulate together to get the final score. This final score could be compared with the middle one. However, the computation loss, the computation overhead during online retrieval is much less than this one. So this is what I mean tensor and COL x-axis models. So it means COL, context on late interaction models. So given such models, we could provide both ranker or re-ranker. What does that mean? For ranker, it means we design a tensor index just for retrieval, just for recall. For re-ranker, it means we use some other solutions for the recall, and then we perform the re-ranker. So which is better? We made some experiments within our database. Firstly, we implement within our database Infinity EMBB. EMBB is a kind of the shorter tensor index. And on the right side, we use brute force. Brute force means it will have the best precision. However, the overhead is pretty high. It's very slow. We can see that in the middle, we use a full text search for the first stage recall and then concatenated with a ColBERT-based re-ranker, the score in terms of NDCG at top 10 is even higher than the index-based one. So we can conclude that tensor index is not deserved to be implemented. So we have done some waste some our time to build this index. So re-ranker is enough. So this is a comparison. The above diagram is the general vector database plus a cross-encoder-based re-ranker. So we can only get top 10 results and send this top 10 results into a model which is run within the GPU to get the final re-ranked solution. Given the ColBERT or tensor-based solutions, we can use some other hybrid search such as the vector search, full-text search, and to get top results and send these results to the tensor re-ranker. So which is better? Because with the ColBERT or tensor-based re-ranker, most of the computation has been finished during offline indexing. So during online retrieval, the computation cost is much lower than the above one. According to our estimation, it's about 2 orders of magnitude faster than this one. Therefore, the tensor re-ranker does not need any GPU. It can run within database. This is the first advantage. And for the second one, we can use within the database, we can re-rank not based on top 10. We can re-rank based on top 100 or even 1,000, which means that if the first stage we have got a very bad result, then we can get better during re-ranker. So it's very, very important for the RAG. So we conclude that the tensor-based re-ranker should be the future of RAG, but not now. Why? Because we are waiting for the infra to be production ready. Okay, so the latent interaction model can also be used for the multi-modal. How to do that? We can use this one. Firstly, we divide the PDF page, a single page, into a series of patches. For example, 1024 patch. What does patch mean? Patch here is just a small box. It's just like token within text. And for each image patch, we represent it with a vector with a 128-dimensional vector. And then there has a Vidora benchmark. So for this benchmark, it is dedicated for the multi-modal recall. And we can see that almost all the leaderboards are tensor-based, are context-to-late interaction-based models. However, 1 year before, the score for this leaderboard is just around 50, around 50, yes. However, since the ColBERT is a French company, right? So ColBERT, after ColBERT is open sourced in the last June, yeah. The Vidora benchmarks, the average score could be improved from 50 to about 80. So currently, you could see that the number one can even got the 90% for the NDCG, yes. So you could see this benchmark, we have lots of categories such as paper, government reports, and all of these multi-modal PDF documents could have got a very high score using the late interaction models. So how does late interaction model-based multi-modal RAG work? We just use this one. For each page within the PDF, we convert it into a tensor using ColBERT or some other context late interaction models, and then store the tensor into the database. And then when we ask a question, this question is a text-based one. So we convert this question into a tensor, and then we use this tensor to search within the database. And then we got the image that contains the answer for this question. And then we send this image to the VRM to get the final answer. So this is the multi-modal RAG based on the COL models. So it's just like this one. Yeah. these two paths. So all of these paths will be provided by RAGFlow. And currently we have only the 3. Okay. So just now I told the tensor is pretty good. The context-related interaction model is pretty good. Why I cannot see it in many products? Because there are many challenges, especially for engineering challenges. Because we store the embeddings for each token or each patch in the database, it will cause a storage explosion. So we need to reduce the storage overhead as much as possible. RAG is actually a co-optimization for the infer and the model side. For the infer side, just now I told that we can use tensor re-ranker to perform better. Tensor re-ranker is very important because if we do not design the tensor index, we just use the tensor re-ranker, we can perform the quantization. We even can use a binary quantization. What does it mean? It means that we can use a single bit to represent a float for each dimension within the vector. It means that the storage overhead can be reduced to the 132% of the original. Also, we need some other facilities, such as the multi-vector index, such as full text index. They are used to the first stage recall and then attached with a tensor-based re-ranker. So this is what we can do at the infer side. On the model side, intuitively speaking, we can use some other solutions. For example, the first one, we need to reduce the dimension for each embedding. A typical dimension of the tensor is 128. We can use some other solutions such as MRL. MRL means Mitri-Oscar representative learning to reduce the dimension from 128 to such as 64. So we can reduce the storage overhead to half of the original. And also we can use some solutions to reduce the number of tokens, such as a ColBERT, which very sort of works. They can reduce the number of tokens. Both of these approaches could be provided. So after all of these solutions can be provided, could we say that we can provide context-based solutions within a product? Okay, so at last, I've got a comparison. The comparison is made the infinity versus the traditional databases with a vector, and versus the pure vector databases, and versus hybrid search. And for the x-axis, it's effect. Effect means that the more number of the approaches for the hybrid search, the better effect you can get. And for the y-axis is for the efficiency. It means it's just a performance. So we can see some familiar database companies for the Elasticsearch. Elasticsearch is the only one that RAGFlow is currently used. Because our own Infinity has not been production ready right now, we plan to make it production ready in the middle of this year. And RockSet is can provide full text search and vector search, and it is acquired by OpenAI 1 year before, with about $500 million. Yeah, so it's very fortunate to become a US company. Okay, so let's come to the next section, Agentic and the future. In this section, I will tell some of the relationship between RAG and the agent. There are many viewpoints that the year 2025 is a year of agent, but nobody says that it's a year of RAG. Why? Because RAG is actually an infer. RAGFlow will provide the overall agent frameworks in the next few releases. Currently, we provide the agentic reasoning. So why agentic reasoning? Most people may think that reasoning should belong to the works of the large language models. However, we are necessary to provide agentic reasoning at agentic layer. Why is this is necessary? Suppose such kind of scenario. So suppose I'm the boss of a company, and I found that our revenue has been decreased for more than 10% last year. Why? And I asked some very smart guys. So I asked him why. And given naive RAG plus reasoning models such as DeepSeek R1, so how does this work? He just search using this question, our revenue has been decreased by 10%, and just search. So what kind of results can be searched? I don't know. And according to the search results, he just think. So what can he got? Does it make sense? I don't think so. I think a much better solution should be I ask this guy to think about it. Maybe it's related with marketing, sales, supply chain, R&D. I don't know. He just need to think, and then he should make the investigation. So agentic reasoning, it just work like this. The question is sent to the large language model at first, and the LM will decide whether it is suitable to decompose the question into several sub-questions. And then some of the sub-questions can be sent to the local RAG to search for the private data for that within the enterprise. And some questions can be used to send to the web search, such as Bing, such as Google. It is very necessary because in most cases, most companies are always being lack of data. So send the question to the web search is just used to complement the knowledge. And also it can be sent to graph RAG because during the construction of the knowledge graph within RAGFlow, we can also extract the questions given any text chunk. And also these questions are also stored within RAGFlow. These questions can be used to refine the sub-questions. So after several iterations, the reflect, we can go to the eventual COT, the chain of thought, dedicated for this question, dedicated for our own data. So this is more reasonable to deliver a reasoning. So this is a screenshot, and we ask the question, Musk and Trump, who has more sense? So we have got the thinking. For this result, I do not use any reasoning models. We just use a general large language model. We use DeepSeek v3, we use general OpenAI. We can also get the thinking. So whether use reasoning models, it depends. I don't know which is better. So you can see that the relationship between RAG and RG is pretty close. And currently, with the popularity of the MCP, we can see that the memory layer for the agent should be very important, and the RAG is actually will be the context memory layer for the agent frameworks. And RAG, RG could be a MCP server for other agent frameworks, and also RAG itself can provide the agent frameworks, which means that it can provide many MCP clients to collect the data from other MCP servers. So the relationship between RAG and RG, between RAG and the agent is sometimes they will collaborate because RAG can be used as a memory layer. Sometimes they can compete. So for RAGFlow, we also provide agents in the next releases. Okay, so in terms of memory, what does memory mean? The essence of memory is actually to provide reasoning capabilities based on the infinite context. So if we use RAG to provide such kind of reasoning capability based on this infinite context, we can provide the filtering and assisted reasoning such as a graph RAG, knowledge graph, context retrieval. Both of these kind of facilities can be looked on as a sparse attention. So in terms of memory, RAG is actually a kind of sparse attention. So it's more sexy, right? So does RAG means equals to the agent memory? We can say that they are almost the same, but have some small differences. Because traditional RAG is used to store some long-term memory. However, when RAG is used to serve for the context memory layer for the agent frameworks, it will store more data, such as session data. So the interaction between multi-agents, all of this session data should be stored within RAG and to be provided to be searched. Also, the retrieval, we have some differences. For the agent memory, they will take some other factor into the considerations, such as the temporal. So the latest message is always the best. And also, we need to introduce the memory decay. It means that we, just like human beings, we must learn to forget something in order to focus on something. So forget is not a bad thing. It's necessary to focus. And then we need some agent facilities such as how the task is decomposed, and all of this meta information will be stored within RG. So how does RAG and memory get evolved in future? Currently, what is available is a upper diagram. So we must have a real-time index database. Real-time index database. So where real-time is here is very important, because for session data, we must search immediately after it is inserted into the agent memory. So without real-time index, it cannot be searched. Search is not query, is not get. Search is search. Search can only be performed based on vector search or full text search or no matter or hybrid search. So you cannot say that you use a MySQL or some other database and you say that it's memory. No, it's not memory. So based on the real-time index database, the memory should be the agent memory. However, we can do something more. This is a diagram in the next part. So from this part, the RG will get evolved from the search engine into attention engine. Attention engine means that we can let the knowledge, we can let the private data to be converted by the large language models into the KV, not KV cache, but KV store. The KV store is stored within the database instead of the GPU memory. And during the token generation, the large language models will decide whether to retrieve the memory from the database, and they got the KV values according to some index, and then compute the attention. So this architecture will be mature within this year, and we will also work on this too. Okay, so let's give a final summary. RAGFlow is an open source product, and we are going to build an ecosystem. Within the ecosystem, we have the infra, and we have a series of small models, including document understanding, document parsing, and some context-related interaction re-ranker, and knowledge extraction, and so on. And above RAGFlow, we also provide agent orchestration. So RAG is very difficult. It's not a problem of LLM ops. Actually, RAG is a database of the LLM area. Okay, thank you. So welcome to visit our GitHub repo. The first one is the RAGFlow, and the second one for the Infinity. Thank you.